In the first part of the video, I did a cube. I should do a fourth power polynomial in this part of the video. And depending on how long it takes, maybe jump into a fraction. And let me do your problem 5 with you, so you can have something in your notes that's part of your homework problem. So first step for number 5, find the x-intercepts. To find the x-intercept of a polynomial, I simply take the polynomial, set it equal to 0, factor out the common factor of x cubed. When I factor out an x cubed, I'm going to be left with an x minus 4. When you set the x cubed equal to 0, you can really just dump the exponent. This is just going to give me x equal to 0, because this is really x times x equal to 0. You could separate each x separately and set them all equal to 0. This is ridiculous, but you can. This x cubed equal to 0 just gives me an x-intercept that has an x coordinate of 0. When I set the x minus 4 equal to 0, I'll add 4 and get a x coordinate of the x-intercept of 4. So I'm doing 5s here. So my x-intercepts are 0, 0, and 4, 0. That 0, 0 is also going to be a y-intercept, and let me do that y-intercept by going f of 0 equals 0 to the 4th minus 4 times 0 cubed. And I can do that in my head. That's 0 as well. So I have 3 points, but one of them is a repeat, so I don't have to show that repeat. Let me start sketching my graph. Anytime I find a point, I like to graph it. Fourth power graphs sometimes are strange. Sometimes you get W's from them. Sometimes you get strange little wiggles in them. I'm not sure I gave myself enough room here, but it is what it is. I'll live with this for now. I'm going to plot the point 0, 0. That's the origin. And then 1, 2, 3, 4, 0. So I've plotted my x-intercept, both of them, and this one's by default also a y-intercept. That's everything in terms of the intercepts. Now we're going to move on and do the increasing and decreasing, all for number 5 and not number 6. So to do the increasing, decreasing maxes and mins, I need to have the first derivative. Don't have it yet, so I'm going to find it. So let me find this derivative. It's an easy derivative. The derivative of x to the 4th is 4x cubed. The derivative of 4x cubed is going to be minus 12x squared. Now let me set the first derivative equal to 0 to get my critical numbers. So 4x cubed minus 12x squared equals 0. I'm going to factor out a 4 and an x squared. When I factor out a 4x squared from the first piece, I'm left with an x. From the second piece, just a minus 3. Now I'm going to set 4x squared equal to 0 and x minus 3 equal to 0. Anytime here, let me just do this properly. I can divide by 4 here and get x squared equals 0. And then the proper way would be to square root. Technically square root plus or minus square root, but since 0 doesn't have a sign, you don't need the plus or minus. This is the proper way to give me 0. But if you just have a single x to any power without an addition or subtraction, it's going to solve down to 0. And this x minus 3, when I set it equal to 0, I'm going to get x equal to 3. So I'm going to create a number line. And on that number line, I'm going to plug infinities, negative infinity, positive infinity, as well as 0 and 3. And I'm going to create intervals. I'm going to create the interval from negative infinity to 0, the interval from 0 to 3, the interval from 3 to infinity, and now I'm going to plug numbers in. In the first interval, I'm going to plug negative 1, middle interval positive 1, far right interval positive 2, into the derivative. So x equal to negative 1, x equal to positive 1, x equal to positive 4 into some version of the derivative. This almost seems calculator-wise easier. So for this guy, I'm going to do f prime of negative 1 is 4 times negative 1 cubed minus 12 times negative 1 squared. And then I'll do the derivative, first derivative evaluated at 1 is 4 times 1 cubed minus 12 times 1 squared, and then the same thing for the 4. 4 times 4 cubed minus 12 times 4 squared. I didn't show the function notation. It's hardly that big of a deal. So first computation. 4 times negative 1 cubed minus 12 times negative 1 squared. I get negative 16, so the graph is decreasing in that interval. And then 4 times 1 cubed minus 12 times 1 squared. Get negative 8, so it's still decreasing. And then 4 times 4 cubed minus 12 times 4 squared is positive 64. There's where it's increasing. So I've got my work cut out for me to write some answers here. So the first interval, it's decreasing. The second interval, it's decreasing again. I think this is called a saddle point, where it's continuous and they double decrease. Could be wrong on that, but I'm pretty sure that's what that's going to be called. And then it increases. So for my answer to part C, the interval where the graph is increasing is just the interval from 3 to infinity. For my answer to part D, the intervals where it's decreasing are both. It's technically at 0, not decreasing. It kind of flattens out there for a second, so I should keep the intervals separated. Now I'm going to worry about E and F, maximum points and minimum points, and not split out and saying the stuff that we did earlier. So first interval, decreasing. Second interval, decreasing. I don't get a max or a min at 0. Doesn't have a max because they don't meet in a caret. It doesn't have a min because they don't meet in a V. But here, where it changes from decreasing to increasing, I get a min. So in terms of my answer to part E, there's going to be no maximum. But there is a minimum, and its x-coordinate is 3. The x-coordinate of the minimum is 3. And now let me find the y-coordinate of the minimum. So the y-coordinate of the min, I plug 3 into the original function. I get f of 3 equals 3 to the 4th minus 4 times 3 cubed. These are all 5s. Duh. 5, 5, 5, 5. So 3 to the 4th minus 4 times 3 cubed, and get negative 27 if I did it right. Now I have a point that I can plot on my graph. So the point 3, negative 27 needs to be shown. So I might as well get it on here. Here's 1, 2, 3. I'm going to go by 10 again. So negative 20, negative 10, negative 20, negative 30, negative 40. Was it negative 27? Duh. 3, negative 27 is my minimum point. Eventually, I kind of steal most of the graph from my calculator and just logic it out as I'm borrowing from my calculator to make sure that increases the right places, decreases in the right places, and has inflection points in the right places and concavity that matches up. So now all the concavity questions, which means I need to get the function carried forward. So the function itself is x to the 4th minus 4x cubed. I don't need the first derivative to answer the concavity questions, but I need the first derivative to get the second derivative, and I need the second derivative for the concavity questions. So let's find that second derivative. The second derivative is 12x squared minus 24x. I'm going to get the critical number by taking the second derivative and setting it equal to 0. Solve by factoring. I'm going to pull out a common factor of 12x. When I factor out a 12x, I'm left with an x minus 2. I'll set the factor of 12x equal to 0, the factor of x minus 2 equal to 0. For the factor of 12x, I divide 12 on both sides and get x equal to 0. For the factor of x minus 2, I add 2 to both sides and get x equal to 2. So now I make my number line that has the infinities in 0 and 2. I'm going to plug numbers into the second derivative to figure out if it's concave up or concave down, and see if I have an x coordinate of an inflection point. So I start at negative infinity, I end at positive infinity. In between, I need a 0 and a 2. My intervals will be negative infinity to 0, 0 to 2, 2 to infinity. In this first interval, I'm going to pick negative 1, middle interval positive 1, far right interval positive 3, just because they're right up to the edges. So x equal negative 1, x equal to positive 1, x equal to positive 3. Into the second derivative, I'm going to plug this number in. So I'm going to go second derivative evaluated at negative 1 is going to be 12 times negative 1 squared minus 24 times negative 1. And then second derivative evaluated at positive 1 is going to be 12 times 1 squared minus 24 times 1. And then second derivative evaluated at 3 is going to be 12 times 3 squared minus 24 times 3. No reason to do that by hand. So 12 times negative 1 squared minus 24 times negative 1 is 36, so it's concave up. And then 12 times positive 1 squared minus 24 times positive 1, negative 12, so it's concave down because it's negative. And then lastly, 12 times 3 squared minus 24 times 3 is positive 36, so it's concave up. Again, you see that duplication that happens all the time when I'm doing these. The way I pick my critical numbers to test, I get the duplication all the time. So the outside intervals are concave up. My answer to 5G is the interval from negative infinity to 0 and the interval from 2 to infinity. My answer to the 5H, the interval what's concave down, is the interval from 0 to 2. So I have 2 inflection points because here it goes from concave up to concave down on either side of 0. So 0 is the x coordinate of an inflection point. And then between the first interval, the second interval, and the third interval, it goes from concave down to concave up. It means I have another inflection point. So because the graph is changing concavity, I get 2 inflection points. So one of my inflection points is 0 comma some number, and the other inflection point is 2 comma some number. And I need to get that sum number by plugging 0 into the original function. So for the 0, I'm going to go 0 to the 4th minus 4 times 0 cubed. That I already did. That's 0. So one of the inflection points is going to be the point we already have marked, the point 0, 0. And then I'm going to do 2 to the 4th minus 4 times 2 cubed. That one I'm not sure on. So 2 to the 4th minus 4 times 2 cubed looks like negative 16. So my inflection points, one point I already have marked as an x-intercept, a y-intercept, and and now as an inflection point is 0, 0, and a new point that I'm going to add to my graph to negative 16, which is just an inflection point. So on my graph, I already have 0, 0 plotted. I'm going to add the point to negative 16 the best I can. Probably I shouldn't have written it there because my graph's going to go through that, but yeah, it is what it is. Now, for my window and my function, let me borrow this from my calculator and make sure it kind of fits. In my y1, I'm going to put the function x to the fourth minus 4x cubed. My x's really can go like from negative 5 to 5 if I want to. I just have to get beyond 4, but there's no reason to change from negative 10 to 10 unless they don't work, meaning unless I have an x outside this window. But my y min needs to at least go down to negative 27. And if I just made it right at negative, oh, you can't even see it. If my y min went just to negative 27, it wouldn't be low enough. I'm going to go to negative 40. And I like the symmetry. So I'm going to make my y max 40. And then I'm going to borrow from my calculator, but kind of talk through it to make sure this is okay. So I have my function of x up arrow fourth minus 4x up arrow cubed, window negative 10 to 10. Now I'm crunching it down negative 40 to 40. The first two intervals it decreases. So decreases, decreases, gets to the minimum point. So here's what's happening right now. All the way from the beginning of the graph to this minimum point, it's decreasing, and you can see that here. First here, it's decreasing and concave up. So the beginning part of the graph, it's decreasing, it's concave up. It got to this critical value, but it stays decreasing. But it changes concavity right there from concave up to concave down. Should actually even be a little flatter than I have it drawn here, but this is not good. Look how it's pretty flat on my calculator. It should be that flat, but it's okay that I kind of should have made it more flat like that and then came down like that, but it's okay. It's not that big of a deal. It's going to continue decreasing, but now it's flipping over from here. So this was concave up and decreasing, concave down and decreasing. Now it's concave up and decreasing, and then concave up and increasing the rest of the way. It should go straight through the intercept. That's the best I can do to copy that picture, and it fits perfectly the calculus, what the calculus said. Decreases, flattens out because I had a critical number there, but stays decreasing, gets to the minimum point and increases. It's concave up, gets to this point, turns to concave down, gets to this point, turns to concave up, and it's concave up the rest of the way. That's a lot, to say the least. Let's do a fraction. So I'm going to do fraction number 8, and you'll see that I have both derivatives written. I'm going to give you derivatives for a fraction. I'm not going to make you find those. So I didn't talk about the domain, but we can do the domain real quickly. The domain is kind of where the graph is going to have a break. To find the domain of a fraction, as I do problem 8, to find the domain of a fraction, it's the same algebra as finding the vertical asymptote, so I didn't talk about this, but I should have. To find the domain of a fraction, you ignore the numerator. That's not going to impact where the graph has a hole or a vertical asymptote. And I set the denominator equal to 0. Either I'm going to say the domain is all real numbers except 3, or I'm going to write an interval equivalent of this. This graph, if you plug in 3 into the function, you'll get undefined. Any other number, if you plug in, you won't get undefined. So one way to write the domain is all real numbers except x equal to 3. The other way is to do it with an interval. And the interval strategy would be to create the number line that we're used to with the infinities, put the solution to the setting the denominator equal to 0 between the infinities, and then create the round parentheses interval. So the interval way to write the domain is the interval from negative infinity to 3. This will be the left half of the graph. Then there's going to be a vertical asymptote, and then the right half of the graph will pick up after 3. This computation's the same. The computation of setting the denominator equal to 0 either gives you a vertical asymptote or a hole. You get holes if the denominator would cancel with the numerator, which it doesn't. So the first feature I'm going to show on my graph is the vertical asymptote at x equal to 3. Time for color coding. So as I go to sketch a graph, I have my x-axis and my y-axis, and the first feature I need to show is a break in the graph at x equal to 3. And to show that break, the vertical asymptote, I usually do it in a different color if I have, and I usually do it with a dashed line. In this graph, this line, the graph won't touch nor cross, although on my calculator, if I set the window in such a way, it's going to get so close to it that you won't be able to see it. But this is my first feature. This is my vertical asymptote at x equal to 3. Some tricks coming here that we haven't got to. To find the x-intercept of the fraction, so I'm given the fraction f of x equals 2 over x minus 3. We learned in the first video to find an x-intercept, you just set the numerator equal to 0. So to find the x-intercept of a fraction, I take the numerator, I set it equal to 0. But there's no solution to this because there's no x in the numerator. This means this graph isn't going to cross the x-axis. There's going to be none or no x-intercepts. There only can be an x-intercept if there's an x in the numerator. Let's move on and find the y-intercept. The function is f of x equals 2 over x minus 3. To find the y-intercept, you plug in 0 for x. This will give me 2 over 0 minus 3, which is 2 over negative 3, which I'd probably write as negative 2/3. It looks weird to have the negative in the denominator. And y-intercepts, the x part is always 0. So this is going to be a point now that needs to show up on my graph, the point 0, negative 2/3. So I'm going to find negative 1 on my x-axis, and negative 2/3 is not quite negative 1. So I'm going to mark it down maybe about here. It's 2/3 of the way between 0 and negative 1. So that's my point 0, negative 2/3. Best I can. And next thing I need to do is the horizontal asymptote. And I don't know if I've got that table handy, but I should have it around, unless I checked it. I don't think I did. Not yet anyways. Give me a second here to find that table for the vertical asymptote. I don't know where it's at, but it's I'm going to show it again. Give me a minute here, because I think it's nice to have that table handy. If not, I'll just talk about what was on that table that I showed in part 1 of the video. Ah, there it is. So for this guy, when I go to find its horizontal asymptote, which is the next thing that I'm asked to do, I look at this. The degree of the numerator is a 0 degree. It's a constant. A constant is a 0 degree. So the numerator is degree 0. And the denominator has an x to the first power term as its highest power of x. The denominator is degree 1. And when the numerator is smaller than the degree of the denominator, the horizontal asymptote is y equal to 0. So no algebra. You could actually do this with limits, but we're doing enough right now that might feel like too much. So no work, just logic it out from that table. The degree of the numerator is smaller than the degree of the denominator. The horizontal asymptote is y equal to 0. And that's actually the x-axis. Let me draw that in right now. Y equal to 0 is a horizontal line that goes through 0 on the y-axis. So my horizontal is the y-axis. So there's my horizontal asymptote of y equal to 0. All right, now all the calculus stuff, increasing, decreasing, maxes and mins, concave up, concaves down, and inflection points. These are nice because they don't have much of anything. So let me write down, well, let me steal in problem 8 what I wrote here. The original function that we're working with is 2 over x minus 3. I'll give you the first derivative on the test. The first derivative, I think this should both say first derivative and not second derivative. Let me fix that in a bit. The first derivative is negative 2 over x minus 3 squared. That's a big deal. It's going to make my life so much easier than having to calculate that. So let me do all the work with the first derivative to get the increasing and decreasing intervals, the maxes and the mins. To get my critical numbers that go on my number line when I have a fraction, I set the numerator equal to 0 and I set the denominator equal to 0. The numerator, because it doesn't have an x, is not going to give a critical number. The denominator, you don't have to worry about the exponent. If there's a parentheses with an exponent, it's just enough to set the inside of the parentheses equal to 0. My critical number is going to be 3. So I'm going to, on a number line, plot negative infinity, positive infinity, as well as 3. Make an interval from negative infinity to positive 3, positive 3 to infinity. 3 is not in the domain of a function. It can't be the x coordinate of a maximum. It can't be the x coordinate of a minimum. It can't be the x coordinate of an inflection point, because if I try to plug 3 in, I'll get 2 over 0, which is undefined. I think for fractions, it's better not to plug in 0. It's better to plug the number right next to the critical number. So I'm going to plug in 2 and 4. I'm going to do x equal to 2 and x equal to 4 to help me figure out if I'm increasing or decreasing. And so I'm going to do first derivative evaluated at 2 is going to be negative 2 over 2 minus 3 squared. I can do this without my calculator quicker. It's ugly on my calculator to enter. This is negative 2 over negative 1 squared, which is negative 2 over positive 1. That's negative 2. So in this interval, the graph of the function is decreasing. Next one, I'm going to plug 4 in and do first derivative evaluated at 4. It's going to be negative 2 over 4 minus 3 squared. That's going to be negative 2 over 1 squared, which is negative 2 over 1, which is negative 2. That's another decreasing because it's negative again. So in terms of my answer to part F, where is it increasing? Never, or none, never, I don't know, none is fine. The intervals, there's no interval. For 8G, it's decreasing in the interval from negative infinity to 3, and then there's a vertical asymptote, and then again from the interval from 3 to infinity. And then if I draw these images here, it's decreasing, decreasing. There's no max or no min at 3, and you're not going to get a max or a min at something that's not a critical value. So there's no max and no min. So for 8H, for the maximum, there's none. For 8I, for the minimum, there's none. Now we don't really have anything to add to my graph other than knowing that it's going to double decrease. I need to now do the second derivative tests, and I give you the second derivative because I don't want you to have to compute that here. So apparently the second derivative is positive 4 over x minus 3 cubed. Don't have to calculate second derivatives of fractions. That's just silly. So I have the second derivative handy. Now I'm going to find the critical numbers. I'm going to set the numerator equal to 0. It doesn't have an x. It doesn't give a solution. Doesn't give a critical number. I'll set the denominator of x minus 3 cubed equal to 0. And it's really sufficient just to set the x minus 3 equal to 0 and get the same x equal to 3. Again, that's not a point in the domain. You can't get a you can't get a maximum at x equal to 3. You can't get a minimum at x equal to 3. You can't get at any point, even an inflection point at x equal to 3, because 3 is not part of the domain of the fraction. There's no point that's going to have an x coordinate of 3 because there's a vertical asymptote there. So I'll take my lonely critical number, make my intervals. In the first interval, I'm going to plug in 2. In the second interval, I'm going to plug in 4. I'm going to take the second derivative and evaluate it at 2 and get 4 over 2 minus 3 cubed, which is going to be 4 over negative 1 cubed, which is 4 over negative 1, which is negative 4. And when I get negatives, the graph is concave down. In the right interval, I'll do f double prime of 4, which is 4 over 4 minus 3 cubed, which is 4 over 1 cubed, which is 4 over 1, which is positive 4. Notice I'm not pulling out my calculator because it's hard for me to enter these fractions on my calculator. It's not so hard for me to do these in my head. So the graph goes concave down and concave up. My answer for 8J, the graph is concave up from 3 to infinity. The graph is concave down from negative infinity to 3. And it looks like, because it's changing concavity, that I'm going to have an inflection point at 3. But in order to have an inflection point, the graph has to be continuous at that point. It's not continuous. It's a point of discontinuity because of the asymptote. So it has none for inflection points. So my algebra or calculus left me really dry here in terms of anything about the graph, other than I know it's double decreasing. So this interval is decreasing. This side it's decreasing. This side is concave down. This side is concave up. And I have the asymptotes and the y-intercept. That's all I have. This is not good, but let me deal with it. Let me write down the function again. So the function I'm going to put in y1. In y1, I'm going to put the function 2 divided by x minus 3. I'm going to do it just like that. For y2, my calculator is not going to show this vertical asymptote. I like to see it. I can't really type x equal to 3 on my calculator. My calculator needs my equations to be solved for y. This is a trick. If you take 1,000 and multiply it by the denominator, it's going to draw a line with a slope of 1,000. It will look like a vertical line. This right here is going to mimic the vertical asymptote, but it's not really going to be the vertical asymptote. If you have a fancy color calculator, in y3, you can type in 0 and you will see the the horizontal asymptote change colors, which is kind of nice. I'm not sure on the window. I'm just going to do a negative 10 to 10. I don't have enough numbers to tell me what to do, and I'm just going to play. As long as I can see where the graph is increasing and decreasing and see where the graph is concave up and concave down, I'll make that window okay. So let me now borrow from my calculator. So put the 2 divided by x minus 3, which is the function in y1. Mimic the vertical asymptote by doing 1,000 times the denominator. And put the horizontal asymptote, which I'll never see. So window negative 10 to 10. I think negative 10 to 10 is going to be fine. If it's not, meaning I can't tell how the graph is approaching the asymptotes, or I can't see the concavity or the increasing and decreasing, then I'll change the window and play with it. But I think this will be adequate. So here it goes. It's decreasing and concave down. It's decreasing and concave up, and there's an asymptote. That's a good enough picture. So I'm just going to try to copy this from my calculator In this first region, it's decreasing the whole way. So it's going down the whole way. It's concave down. It gets to the y-intercept, and then it approaches the vertical asymptote. This is perfect. It's decreasing and it's concave down, goes through the y-intercept, approaches the horizontal asymptote to the left, the vertical asymptote to the right. In the next region, it doesn't have any points to go to, but it's decreasing this whole way. It's decreasing, and it approaches the vertical asymptote and the horizontal asymptote, and it's concave up the whole way. That feels like an adequate picture. That's basically what my calculator gave me. That's as much accuracy as we're going to need for our graphs. We don't need to go ridiculous in terms of graphing accuracy. So we're going to do a part 2, and I'll do one more problem. Maybe I'll do one of your problems. I'm trying to figure out which one to do. But let's pause the video right now, and I'll do a part 3 here in a second.